Hello guys, welcome to my YouTube channel. This is the third video that I'm posting. In this video I want to talk about stochastic optimization, and we want to discuss the calculations done in a paper. Actually, the paper that I discussed in the previous video, which is here. So this is a stochastic problem, optimization problem, because it contains statistical terms, and we should calculate the expected values of the objective and the constraints. So in this paper, due to lack of space, the calculations are removed, but I want to calculate it for you. This is the result. This should be the result that we're going to calculate. And in this journey, we face a normal matrix distribution, which I think would be new for you and interesting. So we go to the solving the expected value, which was in the paper. So the actual term was in this way: expected value of gk transpose theta, g hat k conjugate ck, and here it is. And gk x would be like this: gkx. Here we have gk theta, hk plus fk theta. Okay, so hk plus fk x. So the optimization problem here can be simplified as hk plus fk x transpose hk plus fk. Actually, here is theta fk ck conjugate. So if we conjugate both sides, we would have hk plus fk theta Hermitian and hk fk ck, and the conjugate is removed. So by multiplying the terms, we would have hk Hermitian hk plus hk Hermitian fk ck plus theta Hermitian fk Hermitian hk plus theta Hermitian fk Hermitian fk ck. So here we need a channel model. Okay, hk is equal to square root of beta k multiplied by tk. hk is u would be like this: u 0, and our IRS square root ak would be equal to zeta square root of zeta vk square root and ak0. Here hk is a vector belonging to the domain of n multiplied by 1 here u0 is in the domain of n multiplied by m, and here ak0 equals is a member of complex domain of m multiplied by 1. Actually, here is m multiplied by m multiplied by m, n multiplied by n, and here n multiplied by n. So these statistical terms in the distributions would be like this: hk. You have zero mean and unit variance. u0. Okay, here u0 is a matrix, so we face a normal matrix distribution. For normal matrix distribution, we would have two variances. Okay, and I tell you how it works. Here we have identity matrix of n and identity matrix of m. It means that if we have expected value of u0 Hermitian, you would have in trace of im, and if vice versa, u0 Hermitian u0, you would have im trace of in. Generally, for a normal matrix with this distribution, sigma and psi, x Hermitian equals to sigma trace of psi, and in the other direction you would have psi trace of sigma. And we can prove it here also. For ex Hermitian, the I and jth element would be like this: expectation of sigma, for example, over a xi a x j a star. Okay, we can formulate the I and jth element of x Hermitian with this. So we know that for complex numbers, complex normal variables, like this, xi a and xj a are complex variables, so the result would be like this: ij sigma and psi a conjugate. So by using this sum over a, we would have ij psi a sigma, and this would be sigma, and because we have a, it is the trace of psi. This is psi Hermitian, and because the variance is a Hermitian matrix, actually psi h equals psi. So in this term, x Hermitian, the expected value would be sigma trace psi, and this is a thing we claimed here, so it is proven. And this claim also can be proven with the similar approach. So I was saying that hk0 has a distribution of zero mean and identity matrix of order n, u0 has distribution of mean of 0 and in and im, and you know now that what are in and im. It depends on multiplying x by x Hermitian or x Hermitian by x, and the results are different. And also here we have AK0. AK0 also has a distribution of 0 mean and in. So we have all distributions here. So and also we should define that fk equals u diagonal ak, and this is because here we had, if you remember the last lecture, here we had this. The received signal at user k would be ak theta. If this is the base station, this is the user, and this is IRS. We have a direct channel, HK, user K, and another channel which was the cascaded channel. Here is the U channel, here is the AK channel, and here the diagonal form of phase shift of IRS was multiplied to these two channel and creates the effective or cascaded channel. So we would have AK transpose theta, which was the diag of theta, and U multiplied by the original signal that was intended to be transmitted. So we can replace AK transpose diag theta with this theta diag AK, theta transpose diag AK. So here it is, and UT as before, and UX and X the original signal. So we take this channel as FK theta and name it the cascaded channel, cascaded or effective channel. So F is U multiplied by diagonal of AK. So FK U diag AK. So the optimization problem would be here. Okay, we have it here. You can see that this this FK equals the U diag AK. So if we take the expected value from it, we have HK and no other HK, and HK has HK here has 0 mean. So as we have just one HK, the expected value would be 0. And also for this U and also this AK all has 0 mean, and because we have just one term from each of them, the overall term would be 0. And also for this, because we have just one HK, just one U, just one AK, so the expected value would be 0. And we just have these two terms because we have one HK and two HK. We have here two U matrix and two AK matrices. So we face we face the second moment. Okay, so we face the variance, and variances are not zero here. Variances are not zero. Another thing would be here. If we hk was equal to beta k tk square matrix hk 0 and hk 0 0 in, and we can show that the third term in the statistical form would be 1. I mean hk0 Hermitian is actually in. It is a covariance matrix, and hk0 Hermitian hk0 would be equal to 1. Not 1, but this is here trace 1 and here trace in, so this is equal n. Here we have 1. So here hk has, I mean radical k theta k half hk0 Hermitian tk inch. So we know that here from here, you know, it equals in, and tk is a positive semi-definite and also Hermitian matrix, so the answer would be like this, theta k. Okay, so hk has a distribution of 0 and beta k tk. Okay, so here the second term was u equals to t of irs square root u0 and r irs square root, and the u0, so it has distribution in im, and uu Hermitian equals t irs u0 r irs Hermitian t irs Hermitian, but this TIRS and RIRS are also Hermitian, positive semi-definite. So here we face this term here, U0 RIRS U0 Hermitian. Okay, we can prove another thing here. Generally, if we have x Hermitian, and X is a normal matrix with 0 mean, sigma, and psi as their covariance matrices, we can prove here the I and jth element would be like this: A, B, JB conjugate, so we would have A, B here. So they are complex normal variables. We have here A, B, expected value of xi, xjb star multiplied by AB. This equals to sigma ij multiplied by conjugate form of psi a b. So this equals to sigma ij psi conjugate ab multiplied by ab. Okay, this would be trace of a and psi, and overally we would have trace of a psi. So for this problem, this is the answer. So for this problem, we would have U0 RIRS 0 Hermitian. The answer would be actually U0 had IN and IM as the covariance matrices. So here sigma equals IN and psi equals IM. Here we would have IN multiplied by trace of RIRS multiplied by IM. So here we would have trace of RIRS. Okay, this is the answer. So for this answer, for this term, we would have TIRS square root IN trace of IRS multiplied by trace of IRS. So here we have this IN is neutral, trace is scalar, so we would have trace IRS T IRS. This is the answer. So expected value of U Hermitian would be like this. And also for the other side, U Hermitian multiplied by U, you can see that this equals to RIRS trace of TIRS. So we can see that U has the distribution with 0 mean, TIRS and IRS. Okay. So here we proved this term, and the third term is for AK. AK equals zeta k vk square root AK0. Okay, so expected value of AK Hermitian is zeta k vk square root AK0 Hermitian and vk square root. Also here vk is positive semi-definite and Hermitian matrix. This term equals IN, so overall we have zeta k multiplied by vk. So AK has a distribution of zeta k vk, and also here we have 1. This is the third term here. So we can solve this optimization problem here. The first term is E expected value of HK Hermitian multiplied by HK. HK hk Hermitian multiplied by hk. So here we would have we should use this, and here the third term is 1 actually. So as by writing again beta k tk 1. So for this you would have 1 multiplied by trace of beta k tk. So beta k is a scalar and tk is a matrix, so it equals beta k trace of tk. Okay, this is the first term. The fourth term, that is actually the second term that we should calculate, is theta h, fkh, fk, and ck. fkh, fk, and ck. And fk was u multiplied by diag ak. U at distribution of 0 min, TIRS and IRS, and also AK the distribution of 0 min, and zeta k VK1, VK and 1. So it equals to theta h diag AK Hermitian U Hermitian U diag AK and CK. We can replace these two pairs with each other because it's a diagonal and this is a vector. We can replace the places. So these AKH diag theta h UH U diag CK and AK. Okay, as this AK is 1 multiplied by m and here we have n multiplied by 1, so this is a 1 by 1. This is a scalar. Okay, so for a scalar we can the trace would be equal, right? So by trace I take this AK to the beginning, AK AKH, and an expectation here, diag Hermitian theta UH U diag CK, and here it is. Also, I didn't mention that AK, U, and HK are IID normal vectors and matrices, so they're independent from each other, and so they're independent. Here it equals trace of E. Because they are independent, we can write them separately. Diag H theta, expected value of UHU, diag CK. So we know for this that AK Hermitian is equal to this term multiplied by trace of 1, which equals 1. So it equals theta k VK, and this term equals to trace of IRS, no, U Hermitian multiplied by U, so RIRS multiplied by trace of TIRS. So the answer would be zeta k VK diag Hermitian theta IRS TIRS diag of ck. By taking the scalar variables to the beginning, you would have zeta k trace of TIRS, diag theta IRS, diag ck. And also here we have vk. So here this is the second term, and here we had the first term. So the overall answer would be beta k trace tk plus this term, beta k trace TIRS vk diag Hermitian theta IRS diag ck. So this is the answer. So if we check it out, here you would have beta k trace tk multiplied by zeta k trace t of IRS, beta k trace tk, zeta k trace t IRS, and trace of RIRS, x here is diag of theta or ck, vk yh is the diagonal of theta. So this is the actual term. And also here we have trace actually. Because here we had trace, and here is another trace. So here is a trace. So the answer is obtained, and we learned a lot of things from normal matrix distribution by doing the operations like this. Like this, dividing the matrix into the elements and calculate more easily. And here it is, and the paper used this answer obtained here, and here, and by doing the Lagrange multipliers writes the problem in this way. And this is a convex problem. Why? With respect to theta and ck jointly, the problem is non-convex. Okay, but by using alternating optimization, as I explained in the previous video, we optimize theta while ck fixed, and in the next iteration optimize ck while theta is fixed. So we continue these iterations until the convergence happens. This is the alternating optimization. And why, with respect to each of the parameters of theta and ck individually, the problem is convex? Because if we, this is a constant, okay? This is a constant with respect to theta and ck. So we would have zeta k trace TIRS trace of, for example, with respect to theta, we would have matrix like x multiplied by diag h. So we just have a theta here, and if we take the second complex derivative, you can see that the answer would be greater or equal than 0. So this shows that the problem is convex. And also for the CK case. The only difference would be here. For example, a matrix Y multiplied by diag CK. Taking the second complex derivative from this, the answer would be greater or equal to 0. So this is a convex problem. Hope you enjoyed this session on calculations of stochastic optimization, and I will see you in the next video.